Hi, my name is Sebastian Robitzscg. I'm a senior R&I manager here at InterDigital, and today I'm presenting together with my colleagues Abinaya and Laksh our InterDigital demonstration on Data Unit Group-enabled DetNet routers and controllers for deterministic networking. Now, for the agenda in this video here, we essentially talk about the innovation itself, which I will present, then I hand over to Abinaya to talk about the implementation of our DetNet router, and then Laksh will provide a demonstration of our multi-domain deterministic network approach. So what is our innovation? So the motivation is essentially starting from the point that all applications actually send data that very, very often doesn't even fit into a single IP packet. So we have multiple packets on the line that all form together a single application data unit. Now, this application data unit essentially results in chunks, which is the multiple IP packets on the line, and this group of data unit groups actually form all the individual data packets that are the IP packets on the line. Now, we already see that, that in 5G we have concepts around PDU sets that have exactly the same concept, where, for example, for video, you have multiple, for a single full frame, you have multiple packets all forming the full frame of a video. And if you're losing a single frame, it's actually quite bad because the entire frame then you can't reconstruct in the decoder. So this concept of data unit groups is now applied for any IP traffic instead of just like what PDU sets are about in 3GPP, which is PDU sets within RTP traffic, which is for video. Now, what we're proposing is a straightforward extension to IPv6. So we are proposing a new TLV for IPv6 that is a draft within the DetNet router group in IETF. And essentially, this is composed of a couple of flags and some fields that are all part of the TLV. And here's the list of the individual fields that we're proposing. So this follows a straight mapping into what we can do then for 3GPP, which is PDU sets, but this is all encapsulated in a single TLV for the IP header. So we have, for example, a DOG identifier, which is the number identifying clearly what data unit group we are handling. So all IP packets that belong to the same group will have the same identifier. We also have a sequence number, so we know which packet in the data unit group should come after which one. We have bits that indicate the end of the group. We have importance bits, so for example, certain data unit group packets might be more important than others. For example, if you have control plane traffic for like TLS or TCP that are part of the data unit group, those are perhaps sometimes more important than the actual data packets. It really depends on the scenario, and the application can set this. We have furthermore also the ability to indicate burst, which is start and stop. Now, what can we do now with that? So once we have the ability on the IP layer to essentially understand in the router which packets all belong together, forming the same application data unit, we can now apply pre-auth conditions that are within the IETF DetNet group, which essentially allows us to replicate, eliminate, performing multipath instead of individual packets or service flows for an entire data unit group. For example, we have the ability to really increase in congestion scenarios, or if for example, in a wireless environment, a mobile network, a UE is handing over, we have a couple of milliseconds or split seconds where we do have a bit of packet loss, we can always encourage then the application to essentially perform monitoring, report this to a control entity, and this entity then configures pre-auth conditions in each router to perform multipath or packet replication to overcome any of those resource constraint scenarios in the network. Now, what we're doing in Predict6G essentially is we're bringing this concept not only to a 3GPP domain, but also into a plain DetNet domain. So what we see here on the right is essentially the two domains, 3GPP and DetNet, and this is then exposed through what we call in Predict6G the AI control plane, which is essentially nothing else than a network digital twin, which has a data repository, the AI model management for AI models, and then a network management that takes in all the information about topologies in the two domains, the monitoring data, so packet queuing delays, jitter, latency, throughput numbers. All this data is aggregated here offered to the network management, and then whenever we want to perform or a user wants to perform a new service flow provisioning, this component can then calculate not only the path through the network with all the QoS profiles, if available of course, we can also then calculate automatically the pre-off conditions in case the monitoring exposes any of the congestion scenarios that we had discussed before. And now I'm handing over to Abinaya.
Hello, I'm Abinaya Babu. I'm a research engineer intern at InterDigital. So I'll be explaining about the implementation detail of our demonstration, giving the continuation to Sebastian. So to move further, I'll first explain about the control plane logic that we have implemented. So we have the network digital twin, we have the DetNet controller, and we have the DetNet router. Also, we have the interfaces between the network digital twin and the controller, which are the service flow management, monitoring data, and topology management. And from the interfaces between the DetNet controller and the DetNet router includes the YANG model for the API between DetNet controller and the router. So moving further, the data plane logic that we have implemented the eBPF extended Berkeley packet filtering, which is basically used for filtering the packets, monitoring it, and enabling the pre-off conditions. So basically, we have implemented XTP logic, which basically does the XTP actions, and we have used the eBPF map, which basically helps to interact between the user space and the kernel space. So we redirect the packets from the XTP hook to the user space, the AFXTP hook, using the eBPF maps. And in the AFXTP hook, we have the logic of set cycle time, for which we monitor the packets and we enable the pre-off conditions. So now I'll hand it over to Laksh for explaining the demonstration part.
Hello, my name is Laksh Bhatia and I'm a research fellow at InterDigital. And I'll be showing the demonstration part of this video. So the first thing we'll go through is the testbed topology. We have a UE, a UPF, a DetNet router, and an application. You can see this in the machines over here. You have the application, the DetNet router, UPF, and the UE. And this is our controller that controls the entire setup. The link between the UE and the UPF is a wireless link, which in our scenario will have packet losses, which can happen due to mobility or many other factors in the wireless link. An application in this case is interested in sending downlink sensing results to the UE for a particular task. And we will now introduce packet loss to show you what happens. Here we first show you the topology. As you can see, there are three nodes that we have in the system right now. The first graph shows us the DUG packet cycle count. The second shows us the IPv6 service flow count per cycle. The third one shows us the IPv6 packet count per cycle. And finally, the drop packets at the receiver. Currently, we have a TC running that is dropping 20% of the packets, and you can see that there are a few drop packets in the system. Now we will enable the pre-off, and you should gradually see the drop packets at the receiver going away. And as you can see now that the drop packets at the receiver are now 0. And our packet flows and packet counts are all consistent as we saw them before. And this concludes the demonstration part of the video. Thank you.
This completes our demonstration of our Data Unit Group-enabled DetNet router implementation. Thank you very much for watching and have a great day.